Okay, three quick things before we get started. First, the video turned out to be longer than I expected, so consider watching the video in 1.5x speed or 2x speed. Second, I highly recommend you to continue writing notes for this video as well. Too much information is going to be thrown at you, but if you take nice notes, you'll be able to synthesize the information better. And lastly, my written notes for this lesson are also completely free. Just check out the link in the description. Okay, let's get started. Welcome back. In this video, we will be continuing our discussion of conditional reasoning. I want to begin by discussing this really annoying keyword called unless. And unless works a little differently than the keywords that cleanly map to the sufficient condition like if, all, every, or the necessary condition like then, only if, so on and so forth. It works slightly differently. And the rule of diagramming is as follows. So whatever is attached to the unless will go on the right of the diagram, and the negation of everything else will go on the left. So for example, let's take this statement: unless voter turnout increases, the incumbent will win the election. So whatever is attached to the unless, so voter turnout increases is attached to the unless, that will go on the right. Voter turnout increases. Right, we have our arrow as always, and the negation of everything else goes on the left. So in this case, incumbent will win the election. The negation of it, and from our last video, we know that negation just means adding a not. And I also said that it's sometimes not that simple, and we'll be discussing how to properly negate later on in this video. But for now, we can just go on with adding not. So this becomes the incumbent will not win the election. And you have a standard diagram that you can use as always. And I hope that this heuristic of placing whatever is attached to the unless goes on the right, negation of everything else goes on the left, will help you click and understand intuitively why it works so. A quick summary: we have our arrows as always. Whatever is attached to the unless goes on the right. The negation of everything else goes on the left. And this works regardless of the placement of the unless. So if unless is before everything else, so unless C, D, same thing. So whatever is attached to the unless will go on the right, our arrow, and the negation of everything else will go on the left. Okay, let's start with the meat of the video now, because this is the main thing and probably the most important thing we'll be covering in the conditional reasoning lessons. That is chaining and inferences. So let's start with this simple statement. If someone votes in the federal election, then they are a registered citizen. If someone is a registered citizen, if someone is a registered citizen, then they can get a passport. So we have two if-then statements. So we'll just have two if-then diagrams, and hopefully you understand why the diagrams are like this. Now here's a trick. When something appears as a necessary condition in one diagram and sufficient condition in another diagram, you can chain the two diagrams. So in other words, if something appears on the right in one diagram, like in this case, let's use a different color, like in this case, and left in another diagram, like in this case, we can chain the two diagrams together. So here's what I mean. Let's start with someone votes in the federal election. So this thing right here, someone votes in the federal election. We have arrow, and then we write registered citizen. So we are just copying this diagram for now, nothing too fancy. I'm just going to use a different color. And from this, I can now follow the arrow again. So notice how there's an arrow going from registered citizen to can get a passport. So I can just write this, can get a passport. And this is called chaining. This is called chaining. So what we did was we combined two diagrams into one diagram. And the really powerful thing about chaining is if you can chain two or more diagrams, you can do something called an inference. An inference is basically any statement that's not stated. And from this chain, you can infer if someone votes in the federal election. So let's duplicate. Someone votes in the federal election, then they can get a passport, right? So we basically cut out the intermediary, the middleman of being a registered citizen. And notice how nowhere in the original statements did it say if someone votes in the federal election, then they can get a passport. This is something that we inferred from our conditional diagrams. And this is a super powerful technique that we'll be using over and over again on various different LSAT questions. So I really hope you understand how chaining and inferences work. So a general rule that you can copy down on your notes, that if A implies B and B implies C, then A implies B implies C, and then you can directly also write A implies C. And this is basically a general form of what we did in the example above. Okay, now let's look at a second example. And in this example, chaining is not going to be possible. And I want you to understand why chaining is not possible here. So the example is if someone votes in the federal election, then they are a registered citizen, the same statement as before. Only if someone is a registered citizen can they run for parliament. So only if is a trigger word for the necessary condition. So we know everything attached to it would go on the right, and then everything else would just be the sufficient condition. And here are the two diagrams. So the first diagram is the same as before, and in the second diagram we have registered citizen on the right and run for parliament on the left. Notice how we have not satisfied this rule that we learned right here, that when something appears on the right and something appears on the left, can you chain them? In this example, both of them, both the link between the two diagrams of being a registered citizen is on the right. So there is no way for us to actually combine the two diagrams. And another way to think about why chaining is not possible here is all we did when we did chain was follow the arrow. So when we have A implies B and B implies C, we wrote A implies B, and then we just followed the arrow. And we know that there's an arrow going from B to C. That's why we could write this. In this example, there is no arrow leading out of registered citizen. So there is no chaining that's possible, and therefore there is no inferences we can do. Yeah, so that's it. No more conclusions to make, full stop. And in general, if A implies B and C implies B, so notice how B appears on the right side for both diagrams, neither chaining is possible nor inferences are possible. I want to do one more example, and this example is going to be a little tricky. So try it yourself first if you want. If someone votes in the federal election, I want the highlighter. If someone votes in the federal election, then they are a registered citizen. Nothing new so far. If someone is an international student, then they are not a registered citizen. Okay, so I have two conditionals again. I'm going to diagram them as usual. This is what the diagram will be. Pause the video here and think if any chaining or inferences is possible. Okay, hopefully you tried it yourself, and at first glance it may seem that I have not satisfied the rule of a common link that appears on the right side of one diagram and the left side of another diagram, right? There's actually there is no common link at all here. We are registered citizen and not a registered citizen, but you need both of them to be the same in order to do a chain. But let's check out the contrapositive of diagram number 2. And I hope you remember what the contrapositive is. It allows us to flip the left and right side, but in order to flip, we need to negate it. So this becomes registered citizen. That is the negation of the right side of diagram number 2. And the negation of the left side is not international student. Not international. And now if you can see, if we look at diagram 1 and the contrapositive of diagram 2, we have registered citizen appearing on the right and registered citizen appearing on the left. So we can actually chain the two diagrams, and this is what we get. Votes in the federal election, registered citizen as the common link, not an international student. And from this, we can directly infer votes in the federal election, not a registered citizen. Now, some of you may be thinking that, okay, why didn't we just take the contrapositive in this example? Well, okay, let's try it, right? Let's try taking the contrapositive of number 2. So we have diagram 1 here again, and this is the contrapositive of diagram 2. And notice there is still no chaining possible, because on this side I have registered citizen, but on this side I have not registered citizen. They are not the same. I need the same thing to appear on the right and the same thing appear on the left in another diagram in order to chain them. These are not the same. So the rule still stands that if you have A implies B and C implies B, neither chaining is possible nor any inferences are possible. And this was just a tricky example where we use the contrapositive to do the chain. And hopefully you guys now understand why I taught you the contrapositive in the first place, that it's going to be super useful to make these chains and to get inferences from it. And we'll be doing that time and time again on the LSAT. Okay, feel free to take a break now if you want, but next we'll be talking about diagramming 2 more fun words, some and most. So far, all our examples have been a sufficient condition and a necessary condition, right? All citizens, so let's use the highlighter, all citizens are birthright citizens. We have all is a trigger word for the sufficient condition. This is the diagram, and we also know that this would give the exact same diagram. Awesome. But what about a statement like most citizens are birthright citizens? And this is actually probably a more accurate statement. There are other ways to get citizenship in our countries. But how do we diagram it? How do we capture that in conditional logic? I cannot diagram it like this. This is wrong. This diagram is a diagram for all citizens or every citizen. It's not a diagram for most citizens. So how do we diagram it? And before we talk about diagramming these things, let's begin with some definitions. What does most and some even mean? So most means 50% plus 1. 50% plus 1. And some means at least 1. Let's take an example. If a country has 300 citizens, let me zoom in a bit. Okay. If a country has 300 citizens, a most statement about birthright citizenship would require at least 150 citizens to be birthright citizens. 151 citizens to be birthright citizens, because the burden of proof of a most statements is 50% plus 1. And 300 divided by 2 is 150, plus 1 is 151. If a country has 300 citizens, again, so same example, but now we have a sum. A sum statement about birthright citizenship requires at least 1 citizen to be a birthright citizen. So the only difference between a most statement and a sum statement is the burden of proof. So I have a country and with 300 citizens, and I want to make a most statement. I need to double check that, okay, 151 people actually satisfy what I'm trying to say. But for a sum statement, I only need one person to say. And a sum statement can be satisfied even if every citizen is a birthright citizen. That is completely okay. You just need one to prove that statement. Okay, hopefully this is clear. And now let's talk about how we can diagram these two things. So let's go back to most citizens are birthright citizens. The way we'll diagram it is similar to conditional reasoning, where we have a left side and a right side. So in this case, we have citizens on the left, an arrow, birthright citizens, birthright citizens. But we already know this diagram is incorrect because this expresses all citizens are birthright citizens. So to capture the most, all we are going to do is write most here. This is going to let us differentiate between these diagrams right here, right, and this diagram. This most tells us that this works slightly differently. And the power of boiling down a most statement to a diagram that we're relatively familiar with is chaining works with the same way. So let's take this example. Most citizens are birthright citizens, and every birthright citizen has a verifier. Let me zoom out a bit. There we go. Most citizens are birthright citizens, so that's this diagram right here. And every birthright citizen has a verifiable birth certificate. That is this right here. Notice how birthright citizen is common, right? So I can chain them as usual. So if I chain, it's going to be like this. Citizen goes here, I follow the arrow, and this time it's the most arrow. So I write most, and the common link, which is birthright citizen, which goes in the middle, and then I end with verifiable birth certificate. And from this I can infer as well. So inference just means I cut out the middle link, and I can directly say most citizens have a verifiable birth certificate. And the inference will obviously have most because it's not this arrow, it's our most arrow. Okay. Whew. And once again, life is not that simple. There are many keywords that can trigger a most diagram. So we have mostly, majority, so on and so forth. You can check out the notes as well if you want this in written format. Okay, let's talk about diagramming sum now. And I have another statement here. Some citizens are born in another country. The way we diagram this is going to be a bit different. So I'm going to write the two sides of the sum first. So we have citizens here and born in another country here. Let's use green for consistency. Born in another country. The arrow is going to be this. It's going to point to both sides, and I'm going to write sum to specify that this is a sum arrow. Why is it pointing both sides? This is because the burden of proof for a sum statement is at least one, right? So let's say we have John here, and John is a citizen who was born in another country. So we have John that satisfies that property. Equivalently, we can say that some people born in another country are citizens because the burden of proof is at least one. So I can just use John again to prove this statement. He is someone born in another country and who is a citizen. So that's why I can make, because the sum arrow points in both directions, we can make inferences in either directions. And just as usual, there are many words that trigger a sum diagram. Many, several, few, sometimes they will, not all. They will all trigger the same sum diagram. Here's a table, and you can check out the notes for a neater version of the table. But these are all the valid inferences that we can make given a few diagrams. So we already covered that when we have a most and an implies arrow, I can directly write A implies C. This is the first thing you learned for most. Similarly, if I have sum and an implies arrow, I can use the common link B to directly say A and A sum C. The tricky one is the third one, and I'm going to spend some more time on it. If I have two most statements, I can actually get one sum statement from it, and this seems unintuitive at first, right? A most B and A most C, where does the sum come from? So I'm going to explain this using an example. So I'm going to zoom in again, and let's check out this example. So in a class of 10 students, most students are good at math and most students play an instrument. So these would be my two most diagrams. And my claim is that I can actually make a sum claim between these two. So some students are good at math. So some students are good at math and play an instrument. And this is what the diagram would be. Good at math and play instrument with a sum arrow in between. Why does it work that way? Let's get our 10 students here and visually see what's going on. So we already know that most students are good at math, and the threshold for most is 50% plus 1. So in a class of 10 students, I need 6 students to be good at math. So 1, okay, that's 6, right? 1, 2, 3, 4, 5, 6. Okay. These people are going to be good at math. And I can have more than this as well. This is just the bare minimum of what I need to make a most statement. Second is play an instrument. So I'm going to have 6 students, 1, 2, 3, 4, 5, 6. And these 6 are going to be good at, will be playing an instrument. Play instrument. Notice how there will always be some overlap when I have two most statements. And the overlap will always be at least one. In this example, there are 2 because 10 is an even number. If I had 9 students, I would get 1 in the middle. But the point is, because the burden of proof of a sum statement is so low, it's just at least 1. If I have 2 most statements, I will always have some people who satisfy both properties. And that is exactly why I can get a sum statement from 2 most statements. So hopefully this example helps you understand why this is like slightly different, where we're not just blindly following arrows, we are doing something unique. But this is the only time something unique happens. In most cases, you can just like follow the arrow and it's going to work. I also have a list, and once again, this is what I like hand wrote, the nader list you can find in the notes. These for when you have situations like this, so like a sum statement here and a most statement here, there is no chaining possible, no inferences possible. And I really hope you don't try to memorize these rules. Rather, I hope you make your own examples with a sum statement and a most statement and see why there's no inferences possible. So I'm going to leave that as an exercise for you guys. I never memorized these rules when studying for the LSAT. It just became quite intuitive for me that if I have a sum statement here and a most statement here, there's no inferences possible. And especially with like 2 sum statements, this should be like really intuitive of why no more inferences are possible. So I'm not going to walk through an example. The video is getting too long already, but hopefully you can make up your own examples and think why I am saying that there are no valid inferences possible in these 4 situations. Okay, last concept before we wrap this video up. And I want to spend some more time, as I promised, on negations. So far, we've just been adding a not to negate our statements, and it has worked so far. And that will lead many people to believe that negation is the opposite of a phrase, right? I like ice cream, I do not like ice cream. That is not completely true. This is an incorrect definition of what a negation is. Rather, a negation is the minimum thing you need to disprove a statement. This is a more accurate definition. And I'm going to walk you through some examples to help you understand why the first one is incorrect and the second one is correct. So when I have a simple statement like I like cars, in order to disprove that, I can just add a not. So I can just say I do not like cars. Oops, I want yellow. Come on. I do not like cars. This works for simple statements. And same thing with I do not like to travel. If I add a not to a statement that already has a not, the two nots would basically cancel each other out, and the negation is I like to travel. The fun starts when you have something like all horses are brown. Now, some people might just think that this means we can just say no horses are brown, and that would be the negation of it, right? All we are adding is a not or a no. This is incorrect, because this is not what a negation is. If I want to, let's go back to our definition. Minimum thing you need to disprove a statement. If I want to disprove all horses are brown, what do I need to do? Well, I am going to find a horse that is not brown and disprove that statement. Maybe Gandalf's horse, right? That was white in color. So the negation is not no horses are brown. The negation is some horses are not brown. And once again, the burden of proof comes here. Some, as we already discussed, means at least one. So if I find one horse, Gandalf's horse, that is white in color, I can say that some horses are not brown. That is the minimum thing I need to disprove all horses are brown. Same thing works in reverse. So if I have a statement like some video games are boring, some people might think I can just add some video games are not boring. That is not what the negation is. This is incorrect. Rather, the negation is if I want to prove that if I want to disprove that some video games are boring, I need to basically say that every single video game is not boring. So this is the correct negation. All video games are not boring. And equivalently, I can say no video games are boring. This is just a quirk of the English language. These two things are saying exactly the same thing. But notice it's not simply that I can, like in many cases, I just cannot just add a not and say this is the negation. It's the minimum thing I need to disprove the statement. Let's talk about negating statements that have and ors in it. So we have an and statement here. I am tall and rich. And once again, if you just think that negation is adding a not, you might say I am not tall and rich. This is incorrect, right? Because what does an and statement need? An and statement need both parts of it to be true, being tall and rich. So if the minimum thing I need to disprove this statement is only one of being tall or one of being rich needs to be false. So the negation becomes I am not tall or I am not rich, right? Because or basically allows me to say, hey, at least one of these things is true. So I am tall and rich becomes I am not tall or I am not rich. Same thing with or. Some people might think the negation of I like anime or games would be I do not like anime or games. This is incorrect. The correct negation of an or is an and. I do not like games and I do not like anime and I do not like games. This is the correct negation. Okay. Last, I need to drink some water myself as well. I know the video is getting long. The last thing is to help you understand why are we learning negations. And we already know it's because contrapositives, right? Contrapositives, in order to switch the left and right, we need to negate its side. So if you have simple statements, A implies B, that just becomes not, B implies not A. But if you have an and or an or, we need to be mindful, right? So this is the diagram of the statement here. If I have a voter ID card or a witness, then I can vote. The negation becomes, well, I want to negate the right side. This is a simple statement, so I can just do cannot vote, right? Arrow. And we already know the negation of or becomes an and. So this becomes an and I negate each side of the and. So I don't have voter, or actually I can simplify this a bit. No voter ID card. Oh, I can't spell. Voter ID card. And no witness. This is the correct contrapositive. Notice how the or became an and. And that is it. I think this is the end of the conditional reasoning lesson. By the next video, we will be solving real LSAT questions. Okay, hopefully the video was not that bad. I highly recommend you to go practice now again. This time I've created 3 problem sets for you guys. So go do the first one, review your notes for the areas you're still weak on, then go do the second one. If you're still struggling, come back to this video or check out my written notes, whatever works best for you, and then go do the third one. The 3 problem sets and the written notes for this lesson are completely free. You can check out the link in the description. And from the next video, we will be learning how to solve real LSAT questions. So I'll see you there. Thank you.